Hello everyone, this is Vardman and welcome back. Today we are going to study Master Theorem. Master Theorem is used to solve a given recurrence relation if they are in the form Tn equal to A Tn by B plus Fn, where A and B are two positive constant and A is greater than or equal to 1 and B is greater than 1, and where Fn is a positive function. So Master Theorem have three cases. So first one is if the function fn is equal to big O of n raised to the power log base b a minus t, then it is equal to theta of n raised to the power log base b a, where t is a constant which is greater than 0. Let's see a few example that will give you a clear idea of this case. Let's look at an example. So here we have Tn 8t n by 2 plus n square. So if we compare this with the Recurrence Relation Master Theorem, so E will be equal to 8, B will be equal to 2 and Fn will be equal to n square. And if we take the value of n raised to the power log base b a, this will be equal to n raised to the power log 2 8, this can be written as n cube. Let's see if fn is equal to big O of n log n base b a minus t. So we have fn here, which is equal to n square, and let's find n log base b a minus t. So this is equal to n cube, and we can take the value of t as 1, so this will be equal to n square, and you can see these two are equal, so we can say fn is equal to big O of n raised to the power log base b a minus t, where t is equal to 1. So we can write that the time complexity of this recurrence relation is equal to theta of n log base b a, which is equal to theta of n cube. Let's see the second case for Master Theorem. So if fn equal to omega of n log n base b a plus t, then we can see the time complexity will be theta of fn. So let's see this with an example. Let's look one more example. So we have Tn equal to 16t n by 4 plus n raised to the power 25. So we can get the value of a, which is equal to 16, b will be equal to 4, and fn will be equal to n raised to the power 25. And let's find the value of n raised to the power log base b a, which will be equal to n raised to the power log base 4 16. This will be equal to n square. And if we look at the condition in the Master Theorem, so if fn is equal to omega of n raised to the power log n base b plus t, so if let's see if we can convert into this form. So we have n raised to the power 25 as fn, and we have n log base ba plus t. So here we can see we can write this as n square, and t can be written as plus 1, so this will become n cube. So here value of t we can take as 1. So if we check now, n raised to the power 25 is greater than n raised to the power 3, so this condition satisfies. So n raised to the power 25 is omega of n cube. So we can write that Tn, the final time complexity, will be the function itself. So the final complexity will be theta of n raised to the power 25. Let's see the example. So here we have Tn equal to 2tn by 2 plus n square. So if we solve it, so we will get the value of a equal to 2, b equal to 2, and fn you can see here is n square. And let's also find the value for n raised to the power log base b a. So this will be equal to n log 2 2, which will be equal to n. So if we compare the value of fn, which is n square, and n raised to power log base ba, which is n, so you can see n square is greater than n, and we can say that n square is equal to omega of n. So here if you can see, if fn is omega of n log n base b a plus t, then we can write the function as the time complexity will be equal to the function, which is n square. Let's see a third case. So if fn is equal to theta of n raised to the power log base ba into log n raised to the power k, where k is a constant which is greater than or equal to 0, then we can say the time complexity will be equal to theta of n raised to the power log n base b a into log n raised to the power k minus 1. Let's check few example on this case so we can get a clear idea. Let's see this example. So we have Tn equal to 2t ny2 plus n. So we can get the value of a equal to 2, b is also equal to 2, and fn is equal to n. Let's find the value of n raised to the power log n base b a. So here this will be equal to n log base 2 2, which will equal to n. And if we compare the value of fn and n raised to the power log n base bn, so we get both as equal to n. Now let's see if we can find the value of t, and if we get the value of t, then it will satisfy either condition 1 or condition 2 of Master Theorem. Let's take the value of t equal to 1, and n can be written as n raised to power 1. So for one value it will be 1 minus 1, for other value it will be 1 plus 1. This will be n raised to power 0, and this will be n square. So here n raised to power 0 will be smaller than n, and n raised to power 2 will be greater than n. So for one time it is satisfying big O, and one time it is satisfying omega. So for some value of t it is giving omega, and for some value it is giving big O. So it do not satisfy either of the condition 1 or condition 2. So we will have to look at the condition 3 now. Let's see if we can apply the third condition here. So which is fn equal to theta of n raised to the power log base b a into log n whole raised to the power k. So let's see. So n raised to the power log n base b is n, and into log n. So we can write the power as 0. So this will become equal to n. So this satisfy. So we have proved that fn is equal to theta of n raised to the power log n base ba into log n. So n is theta of n. So now we can implement the condition. So the final time complexity will be n into log base n raised to the power 1. So this can be written as theta of n log n, where the value of k is equal to 1. Let's look at another example. So here we have Tn equal to 2t ny2 plus log n. So here we can write a equal to 2, b equal to 2, and fn is equal to n log n. Let's find the value of n raised to the power log base ba which will be equal to n. And now we've compared the value of fn, which is n log n, and n raised to the power log n base b a. So here we have, so n can be written as n into log base n. So here we can see fn is now theta of n into log n power 1, where the value of k is equal to 1. So the final time complexity will be theta of n into log n over this to the power k plus 1, which is 2.